Okay, so in general, if x and y are joint discrete, random variables with probability mass function. That's, by the way, that's what all this is, right? This is our probability mass function for the joint random variables there. It's got probability mass function, say, call it P. Okay, these are little right there. These are big. Okay. Then the respective marginal probability mass functions are respective marginal probability mass functions. Oops. You know what? I just got excited there. Okay, there we go. We've already seen this. We know what this means. This thing is just defined to be the probability that our big random variable x there takes on the value of little x. Okay, but we now know, the way that we can compute that is by writing it's the sum of p sub x y of x and y over all values of little y. So you're sort of summing out the little y stuff, right? Okay, this makes a lot of sense if you look at a picture, right? If I look at a picture of let's say, like, here's the event that and here's the event that x takes on the value of little x. How many ways can this happen? Well, maybe there's this way, and there's this way, and there's this way. This is y equaling 0 and y equaling 1 and y equals 2 and y equals 3. Okay, so there are a lot of ways for x to take on the value of little x. It might coincide with different values of y, and so to get the area in blue here, the area bounded by the blue region there, all I need to do then, it says, is to add up these pieces, right? Probability that x equals x and y equals 0, plus the probability that x equals x and y equals 1, plus the probability that x equals x and y equals 2. Okay, that's exactly what you're doing here. Okay, so similarly, if I want to get the marginal probability mass function for y, then that's just the probability that y equals y. That's what it means. The marginal probabilities are just the probabilities. Okay, it's as simple as that. But this is giving us a way to distill it out of information about the joint distribution. Okay, and again, so you can sort of think of, we want to think of this as like this one right here. This is a function of little y. Okay, so in order to get this to be a function of little y, I got to sum out the x's. You can say it like that. Sort of strange way to say it, but sum out the x's. Okay. Similarly, what about in the continuous case? If x and y are jointly continuous, random variables with joint density function, f sub x and y like this, then their marginal density functions are yeah. And again, all I'm doing is I'm just writing down the density function for x. That's what the marginal density function is. When we say marginal density function, we're just sort of acknowledging, we're just sort of tipping our hat to the fact that there is in fact another random variable or maybe multiple other random variables out there, and we're just sort of saying, hey, you know, there are these other random variables, but we're just interested in the density function for x, and maybe we're getting it from the joint density function here. So this is just, you know, I'm going to follow the way this tells me to. I've got to sort of sum up the probability mass function over all values of the other variable. So that's exactly what I'm going to do here. I'm going to sum up well, in this case, the density function, the joint density function, x and y, over all values of the other variable. Okay? Yeah. So it's just one integral, integrating out the y, so to speak. Okay? And similarly, the probability density function for y then will be the integral over the reals of f sub x and y of x, y. It's the same density function, but you're integrating with respect to x.